careful to wait just to not start recording until I'm done saying the stuff that could get me in trouble. So, inequalities today that, if you'll recall, I called this Chebycher's inequality in lecture 14, and I looked this up and I cannot find a single book that calls this Chebycher's inequality, so I'm going to blame that on Mike Wu again, I guess. This inequality actually does not seem to have a name in most of the books. Chebycher and several other common inequalities are a corollary of this, but I don't know if this specific thing has a name, but as you'll recall, lecture 14, we did this particular inequality that the probability that g of x is greater than or equal to r is less than or equal to the expected value of g of x divided by r. The way that you prove this is the expected value of g of x, by definition, integral from minus infinity to infinity of g of x times f sub x of x, and that, of course, is greater than or equal to the integral when we only integrate from where g of x is greater than or equal to r up to infinity, as opposed to integrating over the entire real line. And that, of course, is greater than or equal to, if we just, since g of x is greater than or equal to r in that particular domain, that you can pull r out of the integral sign, end up with r times the integral from that particular subset of the real line over f of x, and that's, of course, just equal to r times the probability that g of x is greater than or equal to r. So that gives us this cute little inequality, which is useful in certain circumstances. And there's two corollaries of these inequalities, which give us some of the classic named inequalities, that if g is some positive non-decreasing function and the expectation is finite, then the expected value of g of x over g of a is greater than or equal to the probability x greater than or equal to a. And as I think about this, I'm not sure that the condition that g of x is finite is necessary, because it seems like it's trivially true if that's infinite. But anyway. And if g is a non-negative symmetric function that's increasing on r plus, that is, the positive real numbers, then the probability the absolute value of x is greater than or equal to a is once again less than the expected value of g of x over g of a. And to prove this, you just note that if it's a non-decreasing, if g is a non-decreasing or increasing function, then the probability that x is greater than or equal to a is going to be equal to the probability that g of x is greater than or equal to g of a. So then just use the inequality on the previous slide, and both of those results fall out. Oh, a couple special cases of the inequalities on the previous slide, that these inequalities do have names due to the wide variety of situations where they're useful. If x is positive, then the probability that x is greater than or equal to a is less than or equal to the expected value of e to the tx over e to the ta. That's just letting g of x equal e to the tx in the previous slide. Likewise, for any real number, the probability the absolute value of x greater than or equal to a is less than or equal to the expectation absolute value of x divided by a. More generally, for any p, that probability is less than or equal to the expected value of absolute value of x to the p divided by a to the p. And if sigma squared is the variance, then the probability that x minus the expected value is greater than or equal to a times sigma is less than or equal to 1 over a squared. So inequality number 1 on this list is called the Chernoff bound, which is useful when sometimes if a distribution has a nice form for the moment generating function but doesn't have a nice form for the CDF. And number 3 is known as Markov's inequality, and number 4 is known as Chebycher's inequality. So, I mean, as I said, Chebycher is a corollary of the inequality on the previous slide, but at least books that I could find last night, as well as Wikipedia, always referred to Chebycher as the last inequality on this list, and not the one on the previous slide. So now we'll discuss a couple functional inequalities that, I mean, there's a couple situations where they're useful for proofs and so forth. Honestly, the biggest place where these inequalities come in handy is if you do like high-level functional analysis, which I don't know how many statisticians actually do, much less biostatisticians. I mean, like Hölder's inequality that we'll get to in a minute, you have to use that to prove everything in functional analysis, but it's not something we normally care about. So none of this stuff I view as extremely important. I mean, Markov and Chebychevs are useful for enough things in statistics they're worth being familiar with, like the simplest proof of the weak law of large numbers comes from Chebychev's inequality, for example. But a lot of this other stuff, it's as much mathematical literacy as anything that I don't intend to cover this aggressively in homeworks or exams, but it's worth being aware of just in case it were to show up on a qualifying exam someday. But we talk about LP spaces. This is what I was saying in terms of functional analysis, that a space called LP consists of all random variables whose pth absolute power is integrable. And if you ever take a class in functional analysis, these have all kinds of interesting properties, but it's usually not something that we worry about. And hopefully most of you have seen this before, triangle inequality. If you have two real or complex numbers, absolute value of A plus B is less than or equal to absolute value of A plus absolute value of B. Fairly easy to prove. You'll get to do it on an upcoming homework assignment. Well, anyway, definition of convex function. You may have learned about this briefly somewhere in calculus at one point, but just to refresh your memory, that the formal definition of a convex function is the following, that the mathematical definition is really hard to wrap your brain around. The more informal definition is still somewhat formal. A function's differentiable is convex if and only if it's above all of its tangents, or a twice differentiable function is convex if its second derivative is non-negative. The way to remember convex functions that a normal human being can actually remember is it's a smiley face function that looks something like this. See, draw the tangent line. It's above every single possible tangent line, therefore it's convex. Like I say, the intuition, just draw the graph. If it looks like a smiley face, that's convex. And a concave function is if minus g is convex, and if you draw like a concave function, then it's like a frowny face function, looks like that. My dumb way for remembering this is like concave, that like say it's like the ceiling's caving in on me, then I'd be frowning, so that means that it's concave. I know, dumb mnemonic, but I guess it works. So, for example, g of x is x squared is a convex function. As hopefully you all know, you plot x squared, it's a parabola, smiley face, convex, woohoo. And likewise, log x is concave for x greater than 0. if you'll recall, the graph of log x looks something like this. So it had kind of a really big frowny face, ergo concave. So why do we care about this? Well, for a variety of reasons. For the purpose of this class, we only care about it because of Jensen's inequality. It's actually interesting in other areas of statistics, or at least what I would consider to be statistics, that to find like the optimal estimator, or trying to say like I want to find a function or estimator that maximizes or minimizes some criteria, that in general that's a fairly easy problem to solve if the function that you're trying to minimize is convex, because in a certain sense in n-dimensional space you can optimize your function just by going downhill, as it were, whereas for a non-convex function that's a much harder problem to solve. And I know, like, my old advisor from grad school in recent years has been forcing all his students to take a class on convex optimization just because that's so useful in so many areas of statistics. And I'm kind of bummed that I graduated before this class was offered. It's actually available online. I've been meaning to take it someday. I can send you the reference if anybody's actually geeky enough to care about something like this. But I'm rambling. For the purposes of this class, the reason we care about convex things is because of this inequality called Jensen's inequality, which says basically if x is in L1, i.e. if the expected value of x exists, then and g of x is some convex function, so e of g of x also exists, then the expected value of g of x is greater than or equal to g of the expected value of x, and you get equality if and only if for every line tangent to g of x at x equals e of x, that the probability that g of x is on that particular tangent line is equal to 1. I'll show a picture on the next slide that will hopefully make this clear. So for example, g of x equals x squared, showed on the previous slide, that's a convex function, so that means expected value of x squared is greater than or equal to the expected value of x quantity squared. That's, among other things, this gives us the variance is always greater than 0. And 1 over x is another convex function, so that implies the expected value of 1 over x is greater than or equal to 1 over the expected value of x, at least for positive x. And Jensen's inequality still works if g is concave, but the direction of the inequality is just reversed. That's easy to prove, because if g of x is concave, then minus g of x is convex, and then just multiply both sides of the inequality by minus 1. So this little picture, I'll admit, I cribbed from Wikipedia. It kind of gives the geometric interpretation behind Jensen's inequality. That the basic idea is that if you have a convex function, i.e. like the smiley face function, as you take the original x, which is on the x-axis here, and feed it into g, the whole thing kind of gets shifted to the right. That since it's convex, if you draw the graph, I mean, if the two distributions were identical, then it would just be a diagonal line going from the lower left to the lower right. Since the function is convex, that means that you map a given x to a given y, and it's going to be further to the right for the y than it is for the x, if that makes sense. And here is the math proof of this, that you take that you have the function g of x and g of the expected value of x, that's just some number. So if it's a differentiable convex function, then it has a tangent line at this particular point g of e of x. So we find that tangent line that we call L of x equals a plus bx. So then the expected value of g of x is, since by definition a convex function is above all its tangent lines, that's going to be greater than or equal to the expected value of a plus bx. Like I just said, g of x is greater than or equal to a plus bx due to the fact the function's convex. And a plus bx, of course, is equal to a plus b times the expected value of x. Well, that's just the original function L evaluated at e of x, which of course is equal to g of the expected value of x, because we defined L of x to be the tangent line at g of e of x. So in other words, you plug e of x into L of x and you get g of e of x just by construction, which proves the inequality. So one application of Jensen's inequality is, in other math classes you may have seen these different types of means before. The mean on the far right hand side is what's known as the simple arithmetic mean, or more commonly just the mean. The one in the middle is what's known as the geometric mean, where you multiply all the numbers together and then take the nth root of it. The one at the far left is known as the harmonic mean, where you take the reciprocal of all of the numbers, take the mean of the reciprocals, and then take the reciprocal of all that. It turns out the harmonic mean is always less than or equal to the geometric mean, which is always less than or equal to the arithmetic mean. And we can prove this using Jensen's inequality. The way you do this is, given this set of A's, that you define a random variable such that the probability that x equals AI for 1 over n for all the AIs. And log x is a concave function. So let's say if we take the log of the harmonic mean, just using the properties of the log, that's equal to 1 over n times the sum of the logs of each of the AIs, which is just the definition of the expected value of log x. Because all the points have probability 1 over n, we plug in we're evaluating each of them at log AI, expected value of log x. By Jensen's inequality, that's less than or equal to the log of the expected value of x. The log of the expected value of x is, of course, just the arithmetic mean. So now we've shown that the log of the geometric mean is less than or equal to the log of the arithmetic mean. Its log is a one-to-one function. Take e to both sides, and we've proven the first part of the inequality. I won't bother to go through the proof of the second inequality, but it's completely analogous. So the next inequality is weird, and this certainly is not going to show up on any exam in this class, and I sure hope they would never put this on a qualifying exam either. Really, the only reason we care about this inequality is because you use it to prove Hölder's inequality here in a second. That Young's inequality says if you have 1 over p plus 1 over q equal to 1, and a and b are any positive numbers, then that particular inequality holds. So how do we prove this? Well, let's just define a function of a to be basically the left-hand side of that inequality minus the right-hand side. So let's try to find the value of a that makes that as small as possible. We can do this by differentiating a with respect to a and setting it equal to 0. We end up with a equal to b to the 1 over p minus 1. If you really want to be complete about this, you should check the second derivative to show that this is a minimum. I won't show you the details of that, but then we plug in this b to the 1 over 1 minus p into g of a, we get 0. So in other words, when a equals b to the 1 over p minus 1, then we get exact equality in that above expression, and that's the minimum this function can ever take. So that implies this g of a in general is always greater than or equal to 0. Subtract ab from both sides, we get the inequality that we were trying to prove. Woohoo! And once we've proven Hölder's inequality, you'll probably never have to think about Young's inequality again until you graduate and become a professor and have to teach 660, and then you'll learn it again like I did last night. So, Hölder's inequality. And like I said, I remember taking a functional analysis class as an undergraduate and like everything, you have to prove everything using Hölder's inequality, but I'm trying to remember if I've ever proved anything in statistics using Hölder's inequality, and I can't think of anything off the top of my head. So, yeah, I think this may be one of those things that it's so important in some areas they feel like you should learn about it, but and maybe, I mean, I don't know, our 760, 761 curriculum, maybe you'll use it there, but you won't use it much in this class, I can tell you that much. But Hölder's inequality says that if you have x and y in LP, recall that that means basically that the pth moment of x and y exists, or the pth moment of x and the qth moment of y, rather, where this 1 over p plus 1 over q is equal to 1, then the expected value of x times y is less than or equal to the expected value of x to the p to the 1 over p times the expected value, the absolute value of y to the q to the 1 over q. Equality only if x to the p is some constant multiple of y to the q. And the way that you prove that is you let a equal expected value of x divided, or absolute value of x divided by the appropriate expected value, and let b have a similar definition, and then use Young's inequality, end up with this, then take the expected value of both sides. Is there a question?
Yeah, this might be kind of a dumb question, but are there any values of p and q greater than 1 such that they're not just 1/2 plus 1/2?
Yeah, I mean, I shouldn't try to do math in my head when I'm in front of the room, but remember p and q do not have to be integers here. So, like, let me see, if you say like p equals 4, then q would need to be, what would it be, 4/3, 1 over 4, yeah, then that works. So, yeah, in general, there's infinitely many possibilities. So, we get Young's inequality, take the expected value of both sides. The left-hand side ends up being 1 over p times the expected value of x to the p over the expected value of x to the p plus expected value of x to the q of y to the q divided by expected value of y to the q, so you end up with 1 over p plus 1 over q, which is of course equal to 1. And the right-hand side just ends up being expected value of x times y divided by the thing in the denominator, multiply it out, you get Hölder's inequality, which is what we were trying to prove. And, I mean, I guess one consequence of Hölder's inequality that does come in handy in statistics, as I'll show in the next slide, is the Cauchy-Schwartz inequality, the special case where p and q are both equal to 2. That gives us the expected value of x times y is less than or equal to expected value of x squared times expected value of y squared, with equality if and only if one of them is a constant multiple of the other. And another consequence is what's known as Lyapunov's inequality, which is another one that I forget exactly what it's used for, but in general, expected value of x to the r to the 1 over r is less than or equal to the expected value of x to the s 1 over s if 1's less than or equal to r is less than or equal to s. And yeah, to prove Lyapunov's inequality, you use Hölder's inequality, x to the r with y equals 1, and p equals s over r. And so, just as I say, Hölder's inequality isn't good for anything in statistics. If you use the Cauchy-Schwartz inequality, which of course is a special case of Hölder's inequality, that gives you can use the Cauchy-Schwartz inequality to show that the correlation coefficient is always less than or equal to 1, and with equality if and only if that one of the normalized variables is a constant multiple of the other one. That, like you said, by the Cauchy-Schwartz inequality, expected value of x minus mu of x times y minus mu of y is less than or equal to expected value of x minus mu x squared to the 1/2, expected value of y minus mu y squared to the 1/2. Square both sides, we end up with the covariance squared is less than or equal to sigma x squared times sigma y squared. So so we get the correlation coefficient is always less than or equal to 1. Yay. And one last inequality today, the Minkowski's inequality, which is a generalization of the triangle inequality, that in particular, it gives you that if x and y are both in LP, they have pth moments. Then if you sum them together, that also has a pth moment, and that expected value is bounded by this thing on the right here. And for p equals 1, it follows almost immediately from the triangle inequality. In fact, I think it basically does follow immediately from the triangle inequality. If p is greater than 1, then it's a little bit hairier. That expected value of x plus y to the power p is, of course, equal to the expected value of x plus y times x plus y to the p minus 1, which applied to the triangle inequality gives you that's less than or equal to the expected value of x times x plus y to the p minus 1 plus expected value of y times x plus y to the p minus 1. And then you apply Hölder's inequality twice, first to the first piece and then to the second piece, and you end up with that expression there, which is what we were trying to prove. So, yeah. And Minkowski's inequality, as I recall, that's useful for some proofs as well, but at least if you're like me, it's not something you'll be using regularly in your day-to-day life. So, let me see. It's supposed to be to the medical school in 20 minutes. Oh, what the heck. Hopefully, this won't be too hairy, and hopefully they won't yell at me too much if I'm a couple minutes late. But order statistics, if you've never seen this before, this to me I actually kind of enjoy because it actually is kind of useful for a number of things. That the idea behind order statistics, I'll explain more here in a second, is if like you have a bunch of random variables x1 to xn that follow some distribution, you want to find the distribution of the maximum or the minimum or the median, the one in the middle, or the range, anything like that. The order statistic will give you that distribution, and surprisingly, you can find a nice form for this PDF in the majority of cases. So let's start with one of the simpler cases. Say that we have a bunch of identically distributed random variables, or I should go a step further, independent and identically distributed. We want to find the distribution of the maximum. How would we find that? Well, so using the usual change variables trick, the CDF of z, the maximum, is the probability that z is less than or equal to z, which is just the probability that the first y is less than or equal to z and the second y is less than or equal to z. All of the y's have to be less than or equal to this z. Well, that's just the probability that since they're independent and identically distributed, that's just the product of these individual probabilities. Since they're identically distributed, that's just the CDF to the nth power. So, actually quite straightforward to find the CDF of the maximum in this case. And once we've got that, if we want to find the density or the PMF for that matter, just differentiate, end up with n times the CDF to the power n minus 1 times the original density function. Now we have the density for the maximum. So let's say we want to do the same thing for the minimum. Well, simplest way to do that is that 1 minus the CDF is of course the probability that the minimum is greater than some value, which of course the probability that the first one is greater than that value, and the second one, and the third, and so on. Which, once again, we can find that by just taking the product of the individual probabilities, which of course is just 1 minus each of the individual CDFs to the nth power. So the CDF of W is just 1 minus 1 minus the original CDF to the power n. And to get the density, then once again you just differentiate. So let's say that yi's are all exponential, for instance, and we want to find the distribution of the maximum. Well, using the formula from the previous slide, that's n times the CDF, which is 1 minus e to the minus lambda z, to the power n minus 1, times the original density function, end up with the density on the right there. And to find the density of the minimum, then take n times 1 minus the CDF, so 1 minus e to the minus z, which of course is just e to the lambda w to the power n minus 1 times lambda e to the minus lambda w, which, simplify that out, gives us n lambda times e to the minus n lambda w, which you may recognize. Well, that's just the density of, the density of an exponential random variable with parameter n lambda. We've proven that if you have a bunch of exponential random variables and you take the minimum of the set of exponential random variables, that minimum is just another exponential random variable with a different rate parameter. So another statistic that you might be interested in the distribution of is the range, which is of course the difference between the maximum and the minimum. Well, that's a little bit hairier to calculate. I'll show you the steps that you need to do to calculate that over the course of the next couple slides. So now we'll define order statistics generally. That say you have a bunch of random variables, IID, with some PDF, and we order the observations from smallest to largest. If you haven't seen this notation before, if you ever denote a random variable with a subscript in parentheses, that means the order statistics. That basically you take a sample size n, then you order that sample from smallest to largest. The smallest one is this y with the 1 in parentheses, the second smallest y, 2 in parentheses, and so up, y, the n in parentheses. At the maximum, the y1 is the minimum, etc. And these are called order statistics. The minimum is y1, the maximum is yn. And we want to find the distribution of not just the maximum or the minimum, but some arbitrary yi, and say we also want to find the joint distribution of any possible pairs of these yi's. For instance, if we have the joint distribution, then we could find the distribution of the range, or we could find the distribution of the interquartile range, or some sort of distribution of the median and interquartile range, etc., etc. So how do we do that? Well, we need to find the density of the rth order statistics at a given value y, and this picture is designed to help you try to visualize the motivation for this. that say we have three intervals, the one goes from minus infinity to y, and one goes from y plus dy, some small delta step, then the last interval goes from this y plus dy up to infinity. And say that the probability that you fall in the first interval is p1, the probability that you fall in the middle interval is p2, the probability that you fall in the final interval is p3. Hopefully you recognize that given these three probabilities, that's just a trinomial distribution. Its PMF is given below. So in the event that the rth order statistic lands in that particular range in the middle is the event where you have r minus 1 observations less than y, n minus r observations greater than y, and exactly 1 in this particular interval in the middle. But hopefully you can see the picture at the top of how this should work. So in the trinomial distribution, where the counts for the three groups are S1, S2, S3, that's equivalent to saying we want this first event with probability P1 to happen R minus 1 times, the last event with probability P3 to happen N minus R times, in the event where it lands precisely in this Y to Y plus dy interval happens exactly once. So take the limit as dy goes to 0. That implies that we would want the density of this order statistic to be n factorial over r minus 1 factorial times n minus r factorial. That's just from the formula for the trinomial distribution times the probability that you're less than y exactly r minus 1 times, which is of course f of y evaluated at y to the power r minus 1 times the probability that you are greater than this little delta interval n minus r times, so 1 minus the CDF to the power of minus r times the probability of landing in that interval, which is just the density evaluated at y. And using the formula for like the beta function that I gave a few lectures ago, you can write it like that so that you don't have to write the factorials. And you can do a more formal derivation. This derivation was obviously a little bit hand-wavy, that you can derive the joint density of the order statistics, then integrate out all but the rth order statistic. If you got the optional Goot book, it's in there. I'm sure it's online in some places. If anybody's really dying to see it, I'm happy to photocopy it and stick it on Sakai, but it's just a bunch of ugly integrals that are not that informative in my opinion. So, for example, let's say that y has a uniform distribution, then the distribution of the rth order statistic is just y to the r minus 1 times 1 minus y to the n minus r divided by the appropriate beta function. So that tells us that if it's truly a uniform distribution, then the rth order statistic has a beta distribution with these appropriate parameters. So that's one reason that you care about the beta distribution, that it gives you the order statistics for a uniform distribution. And in fact, like, I used not quite this fact, but a similar fact in an applied paper that I wrote, that to see under the null hypothesis that no clusters exist in a data set, then under the null hypothesis, then a certain test statistic should be uniform. So if you order them, each of those should be beta. So by comparing what I observed to the beta distribution, I could do a hypothesis test of no clusters in the data. So even as an applied person, I have found this order statistic stuff to come in handy from time to time in real life. Quick note in passing that expected value of the rth order statistics, just the expected value of a beta distribution, which is r over n plus 1, which kind of makes intuitive sense that if you split the interval 0, 1 up into a bunch of partitions, the expected value of these order statistics would be evenly dispersed throughout that interval. So you could use the same idea to find the distribution of the median, that say that the sample size is odd, and so we'll say the median is the m plus first order statistic in a sample size 2m plus 1. So using the formula for the mth order statistic, then we get that the median looks like that. And you can use this fact, for instance, that if the original density is symmetric around 0, then that implies that the CDF of evaluated at minus y is just 1 minus the CDF evaluated at y, which would tell you that the density for the median is also symmetric around 0, which gives you the expected value of the median would be equal to 0 in that case. So now let's say we want to find the joint distribution of two different order statistics. That in this case we have yr and ys. We'll assume that r is less than s. Then we would want exactly r minus 1 observations to be less than u, 1 to be in this little u plus du interval, s minus r minus 1 to be between that interval and v, and then we would want 1 observation once again to be in the v to v plus dv interval, and finally n minus s observations to occur above that interval. So now this is a multinomial with 5 cells. That usual formula for that. So taking these limits, we end up with this function of m factorial over r minus 1 factorial times s minus r minus 1 factorial times n minus s factorial times all the appropriate CDFs to the appropriate powers times the densities times the two original densities evaluated at u and v. Kind of long and ugly, but still has a closed form expression for this. You could, heaven forbid, use the same sort of thing to find the joint distribution of 3 or 4 or 10 order statistics together. It would get ugly fast, and I don't know why you would want to do this in practice off the top of my head, but if you ever wanted to do, you could, in principle, find this formula, hopefully with the help of a computer. So, for instance, if we take the uniform example again, if we take the joint density of the rth and s order statistics, the PDF would look like that. Obviously, under the requirement that u is less than v, because the rth order statistic has to be less than or equal to the s order statistic. So now let's say we want to find the joint distributions of all order statistics together. That's actually not too bad, but say you have a multinomial with 2n plus 1 cells, where we have 1 observation in each of those intervals, in 0 in any of the others. It corresponds to a multinomial where there's 1 and exactly 1 event in each of the possible classes. Well, that's just going to be n factorial divided by 1 factorial, 1 factorial, 1 factorial, 1 factorial. Just n factorial times p1, p2, p3 up to pn, which is just the product of all the individual marginal densities. So it actually turns out to be surprisingly not ugly. It's just n factorial times the product of a bunch of marginals, is subject to the constraint that everything is in the right order. So uniform distribution example once again, that if f sub y has a uniform distribution And the joint distribution of all the order statistics is just n factorial, assuming that everything's in the right order, that u1 is less than u2, less than u3, up to un, forces 0 if anything is out of order. So after all that, we can now calculate the distribution of the range if we really want to, that if we let r equals 1 and s equals n in the joint distribution of the rth and s order statistics, that gives us, then we can find the joint distribution of the min and the max. That will give us n factorial over n minus 2 factorial times the difference of the CDFs to the power n minus 2 times the PDFs evaluated at u and v. So you can do a transformation where you let r equal the range, w equal just the min, then that will give you the Jacobians equal to 1. So to find the joint distribution of r and w, using the change of variables formula, it looks like that particular expression. So if you want to find the density of r, then you just have to integrate the above expression with respect to w. So kind of ugly, but doable, particularly if you have a computer that will do this integration for you. So if y is uniformly distributed on 0 to 1, then to find and using the formulas from the previous slides, the density for the range, you just integrate n times n minus 1 times r to the n minus 2 from 0 to 1 minus r. That's, of course, just equal to n times n minus 1 times r to the n minus 2 times 1 minus r. And note that, once again, the range of uniform 0, 1 random variables, again, has a beta distribution. And so you could calculate the expected value of that or just look it up from the beta distribution, ends up looking like this. So yeah, I'm supposed to be in the medical school now, and luckily this is my last slide, so this is a good time to shut up. Any questions about any of this? Okay.